we'll get this thing kicked off. I hope everybody's got their food. If you don't mind the conversation while I'm starting, if you want to get dessert and you forgot to, it's back there. It looks really good. We'll thank Yvonne and her crew for providing lunch. It's always great. We've got a few things to discuss today. We're gonna announce the scholarship recipients. A couple of those people here to receive those scholarships. We'll pass the mic to Alan Portmiller here shortly to do that. In the meantime, I want to go ahead and remind everybody of next month's meeting. I apologize, I don't have the date off the top of my head, but I bet somebody here does.
Jeremiah.
Mike. Check your calendars, check the API website. We're also tentatively scheduling the API golf tournament for early September. We're trying to secure those dates and compare those up with some other events that are taking place that same period of time. So once we get those secured next month, we'll have a date nailed down. I'm always encouraged to remind people of a different organization's event for tomorrow, the Pistol League Shoot. For those of you who are not involved, there's still time to sign up for that. Other than that, so we've got the scholarships, and our speaker today was Sammy Graham or Jeremiah. Sorry, Sammy's pointing because he tells me he's retired about every week, but somehow I'm still involved. No, actually, now that I think about it, can we take a second and recognize Sammy Graham for all of the efforts he put in as program chair for the last 100 years? Everybody was laughing so loud they didn't hear how long that term was. That's a good sign. No, Sammy has done a fantastic job. I really can't say enough, and everybody within the board agrees that that's the most difficult job, and for Jeremiah to take that over, round of applause to you two, buddy. Thank you very much. So, without any further ado, Alan, if you'd come up and introduce our scholarship recipients present today. We'll have a couple more next week. Just recognize them, and then Jeremiah, got to get through that. Jeremiah will come up and introduce our speaker. Thank you.
Thanks, Randall. We had 38 applicants this year, which is pretty high, pretty good response there. The first one we have is Layman Barnett. That's here. He's a petroleum engineer, grad student at OSU, and wants to be a Golden Well Planning engineer. So, you want to come up here? The next one is Weston Francis. He's a legacy scholarship freshman at OU in pre-med. Said he wants to be a physician. And Ashton Francis, another legacy. He's a junior at OSU in chemical engineering. And he's going to be a growing engineer. And Madison Blakey, a legacy scholarship, a sophomore at OCU in nursing, and wanted to be a labor and delivery nurse. So these are 4 of them. We gave out 10 scholarships this year. And you guys all earned it. Like I said, there was 38 applicants. So give these guys a round of applause. I'll turn it over to Jeremiah.
Thank you. So we have Wesley McDaniel with Liberty Frac coming to speak today. Spent the last 3 years with Liberty. He's over ops and sales for the Rockies division. Specialized in artificial lift and production. Prior to that, he was with Weatherford, working as the long stroke production manager. Graduated out of Houston with an economics and business degree. And he's from Longview, Texas. It's all you, sir.
Thank you.
Thank you, Wes.
I talk pretty loud. Do I need a microphone? Because I prefer not to use it, but I can in the back. Do you need a microphone or no?
Remember, he said Sammy was 100 years old, so he might
I'll
not be
use
able to
it
hear.
just in case. But and quick disclaimer: Rod Moore promised me. I live in Denver. He told me by coming here they'd have Remington 7 mag ammunition that I could buy here. If they don't have it, Rod's in a lot of trouble.
Which I know nothing about.
How many production operations or people have been are currently in or doing production or familiar with it in this room? Okay. kind of talk about, we're going to be talking about mechanical long stroke pumping units. A couple things when I say a pumping unit, we're talking about a beam unit, right? A pump jack, when we talk about comparisons of that. When I talk about long stroke units, it'll be a linear mechanical long stroke unit. I'll go into some differences. I know there's a few different types of long stroke units now in the market. We've seen some pump jacks now that are coming out, 25, 60, 300-inch stroke units. That would be considered a long stroke unit, but it's a pump jack. We have hydraulic pumping units that are on the market right now. I can answer some questions on those, and then we'll talk about mechanical long stroke units. And I promise I'll do my best to not make this a sales presentation, really just talk about the technology. We'll use Liberty Lift, our products, in case studies and things like that, but really try to make it more of a technical conversation. And as we go, I only have about 20 minutes to talk, so it's going to be kind of some broad strokes, right? But if you have any questions, guys, I'd much rather this be a conversation style presentation instead of me just beating you to death by PowerPoint. So stop me in any way that we go. Has anybody ever run any mechanical long stroke units? A Rotaflex, a Liberty Lift XL, Dynapumps, anything over a 300 or 220-inch stroke? Anybody? Okay. So what we'll talk about today, the value add systems for these units, where they kind of fit in the artificial lift space, the value that they bring. We'll talk a little bit about the parameters of the unit so we all are on the same page. We'll talk about how we're transitioning to rod pumps sooner in the lift cycle. The big value system for this is the elimination of intermediate lift systems, right? Improving pump efficiency with long strokes, how we do that, mechanical aspects of it that allow us to do that. We'll talk about reducing lifting costs, and then some best practices that we've seen, that we've learned with long stroke units since their kind of, inception back in the 80s, right? So kind of the key parameters we'll talk about as it relates to API. All these units, kind of the same nomenclature in the market. We've got the smallest style units, a 320, 360, 291. For those of you who don't know, real quickly, 360 is your gear reducer torque rating. The second 3 digits are your structure rating and your fixed stroke length. But 320, 260, 291s, 320, 500, 306-inch strokes. 320, 500, 366-inch stroke. These are fixed strokes, unlike a conventional pumping unit where you can change your stroke lengths by changing your wrist pin hole. This is a fixed stroke. And then now the largest long stroke pumping unit on the market, a 320, 550, 416-inch stroke length unit. What we're looking at here. So I'm not really focusing on any particular basins, not the scoop and the stack. We'll talk a little bit about Permian case studies. We'll talk about Bakken case studies. We could talk about the Weld County, the DJ, so kind of a broad stroke. But this is kind of your typical, your unconventional decline curve. Obviously, this changes based on which basin we're in, but I think it's kind of fair to say, we've got a frac flow back for the first couple of months. Natural flow, some point on the well, sometimes that's 2 months, sometimes that's immediate, goes to lift. Then we're seeing an early artificial lift period, after around 8 months to 36 months. Generally that's been ESP, gas lift, and jet pumps is what we're seeing. And then later in artificial lives, whether it be jets, gapple, gas lift, mostly rod pumps, right? So we're seeing with long stroke pumping units, we're trying to take the production curve and going from rod lift around this stage cycle to a little bit earlier in the lift cycle. And again, that's just dependent on the well, right? It's not a cookie cutter system, but it's all dependent on your liquid production, GLRs, casing size, tubing size, a lot of different variables. These are kind of the production rates we're seeing with long stroke pumping units. Again, it's variable, 7-inch casing, 2 7/8 tubing, or 5.5, 2 7/8. Around assuming 80% pump efficiency, we're able to lift 1,200, 1,000 total fluid for 4 and 16-inch units. That's assuming the kickoff point, maybe 9,000, 10,000 feet. With a 366-inch unit, we're seeing mostly around 800 total fluid. Whoever's computer says you're getting a reminder tomorrow. 800 total fluid with 7-inch casing, 2 7/8, 366, 680. Again, this is different pump sizes, 2 3/4, 2 1/4 tubing pumps, 2-inch pumps. You know, using a smaller unit with 5.5, maybe 2 3/8 slim hole, we're seeing 324. It's using an 1.5 inch, the largest size insert pump we can get, and 2 3/8. And the type of rod tapers we can use. You know, continuous rod, 87, 86 tapers. We can use on the slim holes, 7 taper or 76 tapers. Fiberglass is not really too conducive with long stroke units. That's kind of a little bit of a change in terms of conventional use. We'll use a beam unit, a pump jack with glass to lighten the structure rating, try to create a little higher modulus of elasticity, and then we can extend our downhole stroke, stroking a unit with a short stroke very fast. You can actually extend some of your plunger travel with glass rods in the hole. With a long stroke unit, just due to the sinusoidal motion of that unit, glass becomes challenging. You end up losing probably about half of your downhole stroke. That's why you won't see a lot of fiberglass rod designs of long stroke units. We'll use it a little bit, maybe a 10% taper at the top just to lighten if we're exceeding a structure rating, but it's mostly all steel or continuous rods that we're using. We have seen some carbon fiber rods coming on the market. We've tried that a little bit. Their elasticity is very similar to fiberglass rods, so not seeing being used too heavily. They're also very, very expensive right now, but I think you're going to see probably that's another thing you're going to see in the market here coming soon is carbon fiber rods coming. Any questions on the production parameters, guys? I don't know if for you, what are you seeing with your production rates for your SSI units?
1,000.
1,000,
But it's in 7-inch.
7-inch casing. Yeah, so that's a big thing with any pump group. 7-inch casing, we're always seeing more production. It's not due to the casing size. I mean, you can use larger pumps. It's really gas breakout. Is that what you're seeing?
Yeah.
And that's going to be the biggest push for long strokes. What we're seeing with unconventionals is really the system the system can do this. Now, how do we achieve it with gas and flux, different slug flow, things like that. So here's some sample designs of kind of what we can do with at an 8,000 foot well, tubing anchor depth, assuming a high pump intake pressure for this. Again, with a 366 unit, we're forecasting 85% efficiency at a 8,000 foot well, 900 total fluid, right, using a pretty large pump. It's kind of a little bit more of a case study what we did with an operator in the Permian Basin. This was a Ward County, Wolfcamp A and B, Bone Springs, setting a pump depth at 10,000. We were using 7-inch casing, 2 and 7/8 inch tubing. Rod tapers were a little different. Well 1, we used an 87 taper at just 1 inch and 7/8. Eliminated 3/4 inch rods with weight bars. 86 was 1 inch at the top, 3/4 inch rods at the bottom with weight bars, and the same for well number 3. This operator was targeting 700 total fluid for the first 2 wells and 600 total fluid with the second one. And after 6 months of production, we were able to achieve 730 with well 1, 479 with well 2, 554 with well 3. So pretty close. You can see the cards there. Just some of the case studies that we put together. Big thing about these units too, your SPM, if you're talking about, not only achieving production, but also doing it in a way to eliminate cycles and rod reversals. These units, you're never going to stroke these over 4.5, 5 SPM max. With the use, now we've learned a lot about variable frequency drives and how we can, instead of just having one fixed speed, these stroke units have 90% of their stroke is in the vertical portion, so we can increase and decrease speeds pretty rapidly, but just learning what the system can handle. You're obviously taking a look at structure ratings, but you're also wanting to look at polish rod velocities, want to make sure you're keeping your rods in tension, plunger travel down hole, and then gas separation also.
Is the speed the same on the upstroke and the downstroke?
The question was, is the speed the same in the upstroke and the downstroke?
Yes.
It can be. If you're using just a POC or you're just powering up the unit, it's going to be operating at a fixed speed. So when it transitions from the upstroke and the downstroke and the downstroke, it's going to be a fixed speed just based on your shift size. You're going to calculate it, and at moment of reduction, it's going to stroke not to exceed probably 4 SPM.
But it's not like the Lufkin Mark II, where it accelerates in the downstroke.
No, sir. Based on that geometry of enhanced geometry, front-mounted geometry, just due to the crank inertia, that unit's going to accelerate naturally. On the downstroke, it's going to have a slower upstroke, much faster downstroke. These units are never going to change speed, so you're going to have constant polish rod velocity on just when it's operating. You can with VFDs, you can manipulate that with a Lufkin Mark, just like you could a long stroke unit, but VFDs have different parameters. Like a SAMS controller, you create it based on hertz and amperage. You change your speed by adjusting the amperage based off the max percentage of your highest stroke speed. And you can manipulate that in the stroke cycle and change acceleration and deceleration points. A Weatherford Well Pilot changes degrees based on a circle. You update your VFD and you change it 0 to 360 degrees. You set points in the degree system and accelerates and decelerates. Spirit drives much like a Lufkin drive. So all the VFDs do the same thing. It's a little different how you change it, but you can manipulate speed. And for those of you that are in production that do VFDs, I encourage you. And when you work with service companies like Liberty Lift, that's one of the things we help optimize is using your VFD so you can really maximize your production based on stroke. It's really kind of that work smarter, not harder kind of mindset where I can actually slow my pumping unit down, extend plunger travel, increase your pump fillage from maybe 60% to 90%, or let's just say 60% to 80%. You've actually slowed down your unit, but you're probably increasing production maybe by 15, 20%. So that's a big thing with, especially with gas, because you're always trying to create your system where your fluid velocity is slower, so it allows gas bubbles to naturally rise. Any gas separation system that we have on the market, really all that's doing is manipulating gas so it can just naturally separate. Thank you. So kind of going this, for those of you that don't really know how a long stroke unit works, it's very similar to a conventional pumping unit as we're going from a rotary motion to a reciprocating motion. It's just done inside of a tower. And the benefits of these units and why we use 320 reducers instead of 912 reducers or 1280 reducers or 1824 reducers is really just due to the mechanical design. So you have right here is a drive sprocket. That's your rotary motion, right guys, that operates around here. And I won't go into too much detail on this. If you have more questions, I can talk to you about it offline just for the sake of time. But on a conventional 912, 427, 192, you have a pretty large crank arrangement, right? From that bull gear, your low speed shaft, to extended out on your radius where the furthest reach of your counterweight goes. It's probably about, depending on the unit geometry, it's a 9-foot, 10-foot swing radius, right? That's a lot of torque, a lot of inertia needed just to turn that crank arrangement. On a long stroke pumping unit, we have an 18-inch moment arm. So from your center of your low-speed shaft to the outside of your drive sprockets, 18 inches. So you're not using any torque to generate movement on this unit. So that's why we use 320 reducers. So that translates to smaller prime movers. An 1824 or a 1280, you're probably using 125, 100 to 200 horsepower motors. We can use 100 horsepower motors on these systems. And based on that turnage, we really reduce dynamic loading on our sucker rod string. Does that kind of make sense to everybody? I can talk to you a little more about it. But 90% of the surface, 90% of our stroke is all in the vertical portions.
Is your electric bill the same as you put like a conventional lot pump?
It's going to be about the same. I mean, from a 640, we're probably a little higher just because you're using probably a 60 horsepower motor or even a 50 or even smaller on a 640 conventional unit. But if you put comparisons in terms of production, we're really where long stroke's niche are is replacing ESPs or higher other intermittent lift forms, right? So if you're on a 200 horsepower submersible, you can switch to rod pumps at 1,000 total fluid. You're going to reduce your operating costs just from a kilowatt hour usage pretty substantial. Then you can just go to, you're reducing pool costs as well. An 1824 or 1280 pumping unit, it's pretty similar, maybe probably a little less, just depending on the application. Again, it's all kind of production forms. If you can lift a well with the 640 pumping unit and you know it's not, let's just talk about production only. Let's take out deviation or gas or corrosion or anything else, but if you could lift a well with a 640 pumping unit, there's probably no reason why you need a long stroke unit unless you just can't keep rods and tubing in the hole due to deviation. It's just not, you're as an operator, it would never see the return on investment on that if you're lifting 100 total fluid. It just doesn't make sense. So it's a higher lift form method. So how do we reduce lifting costs? First is intermediate lift replacements, right guys? It's reducing pull cost. If we can go from, depending on the well, we have some operators that go straight to rod pump with long stroke units, lifting 700, 800 total fluid. We've got some operators that will transition from one ESP pool to go to rod pump. If you can eliminate those intermediate lifts, so you can go to one transitionary lift form, maybe submersible, high volume gas lift, annular gas lift, jet pumps, and go to rod pump at 1,100, 1,200 total fluid instead of replacing 3 different lift forms before you go to rod pump. That's really your reducing lifting costs, right? Is to get to rod pump without having to transition and do a bunch of tubing pulls. We talked a little bit about how we reduce surface power consumption. Again, that's just going down to smaller prime movers from expensive, we do jet pumps in our business as well, but we're lifting jet pumps or submersible 200 to 250 horsepower systems, and they don't downsize very well. So if you can transition off of those systems and go to rods, your OPEX cost is going to be reduced. Then we'll talk about rod and tubing. Low and slow stroke reduces overall rod and tubing wear, guys, and it's the biggest way to think about it is just cycle reduction. If you looked at maybe a 306 long stroke unit compared to a 192-inch stroke unit, production's the same. Both systems could probably do 550 total fluid at a 7,000-foot pump depth using 2-inch inserts. But with a long stroke unit, we can do it at 4.2 SPM. At a 192-inch unit, we can achieve it at 7.5 SPM. So that's 6,000 cycles a day compared to 10,000 cycles a day. You calculate that to a month and then year. We're saving about 1.6 million rod cycles in a year, guys. API designated sucker rods do not have an infinite life. Even in perfect conditions, any sucker rod manufacturers, it's 10 million cycles. And that's not assuming any corrosion or any different challenges in the well. We're seeing in different different basins, some rods will make a life of 6 million cycles, some are 4 million, some are 10. So if we can extend rod life just by reducing cycles, it's going to it's going to reduce your lifting costs. Then improving compression ratio. That's the biggest thing we talked about gas. There's 2 things where long stroke units are going to do to support with gas separation. One is just slowing your fluid velocity down so gas can naturally separate out of solution. We're trying to get that below 0.4 feet per second. And just improving compression ratio. The longer your stroke, the more compression ratio we have in our pump. Our rod pumps are going to come off seat when your stroke is coming down. Your traveling valve is going to lift in 2 ways. It's automatically going to hit fluid, or it's got to overcome the hydrostatic head above your plunger. So the more compression you have, the longer sweat volume you have, the more opportunity your traveling valve is going to come off seat much sooner. Then if we can minimize your unswept volume, which is your spacing, that's even going to improve your well even more. Then how do we reduce fluid velocity? We're trying to calculate gas to get it below, really, depending on densities of fluid, we're trying to get gas out of separation about 0.4 feet per second. What are you calculating for here when your wells?
0.4.
0.4?
Yeah.
And that's pretty average. We're seeing in some places, and that's not slug flow either, guys. We're just talking about, gas out of liquid, right, to get separated. When you have higher fluid volumes, it's going to change. But say you have a fluid level of 100 feet, 200 feet above your pump. Around 0.4 feet per second is a pretty good industry term where we calculate. When we design gas lift systems, we're using that. So if we can slow these units down to 3, 3.5, 4 SPM, just much more. It's much simpler to get gas to come out of solution just doing your gas separation system.
How do you adjust the rod spacing?
At surface,
Yeah, at surface. If you wanted to lower the rod strength to reduce that unswept volume in the lower portion of the barrel assembly, how do you lower the rod strength?
did everybody hear that question?
No.
Question was, how do you adjust and account for surface space out? And what do we do to work on that? The question is make sure you have plenty of ponies in the hole when you install it. We're designing like on a 366 or a 416. We're doing 46-foot polish rods at service. You want to make sure you have 6 foot of non-spray. Now you got two rods. You generally have 2 polish rod clamps you're putting on a well. You've got a wireless load cell. You may have a rod rotator. So even just your natural jewelry,
Then how do you lower the rod strength?
you're going to use it with a service rig
Okay.
or a toadstool. Everything now it's a crane. You're putting all operators, service companies have a crane. You put a rod elevator and you manually do it.
Okay.
And the reason I say that, you want to have plenty of pony rods in the hole because, when we're coming off of a well, maybe on a submersible, you go down for 2-3 weeks, you're going to have just your well fluid naturally rise in that time. So even when a workover gets on a well, they're going to space that well out based on that, that given fluid of that day. You've got a dynamic well bore. So even in 30 days, you may be off spacing by 5 to 15 inches, we've seen. So for engineers who are designing rod pump systems, it's real important, we stress it a lot for service companies, is do multiple iterations on your rod designs. Do a design level where you're calculating the pump intake pressure, maybe 1,200 or 1,500 with a fluid level that's 5,000 feet above your pump. And then doing a design where you're in pump off condition so you can see kind of what your rod compressions are going to do, because it's going to change. Your bottom minimum stresses are going to be completely different with a higher fluid level than they are in pump off condition. So do multiple design iterations and just make sure you have plenty of surface stroke to utilize and plenty of pony rods and polish rods to manually make surface adjustments, because it will make or break the efficiency of your system. We're trying to, you want to get your traveling valve to your standing valve absolutely as close as possible without tagging the top. I've got a slide I was going to talk about that a little bit, so good key in question. But talked about best practices, a good design, installation, obviously match reservoir with pump capacity, operation, chemical programs, maintenance, downhole gas separation, and we talk about rod pump spacing. If you've ever has anybody ever been to a rod pump shop and watched your rod pumps being built? You have I worked in a pump shop for a year and a half for production sides. I strongly encourage you to get out and troubleshoot and watch your rod pump spacing being built out. Those guys are spacing and building your pumps. Kind of our best practice recommendation, you want around a 2-inch spacing recommendation, because if they cut your valve rod wrong, you may not be able to change anything, and you could have a 10-inch spacing in your pump and not even know about it. And it's going to really affect pump efficiency. So if you don't have a troubleshooting program and a failure analysis program with your rod pump shops, I strongly recommend it. Polish rod sizes, and then multiple design iterations. I think I talked about that. But we'll talk about spacing again, kind of when in the next thing. So trap gas expands as the pump upstroke begins, which delays standing valve operation. So what you're trying to do is get your traveling valve as close to your standing valve as possible. And as fluid dynamics come into your well bore, your downhole stroke is going to change. You're always going to have a fixed surface stroke, whether it be 192 inches, in this case a long stroke 366 inches. But you take harmonics, fluid, different restrictions, you may see a 300-inch stroke at the bottom. You are going to see a much improved net downhole stroke and long stroke units as you would a conventional unit. It's much easier to manage. Mainly you can just use higher rod tapers. It's a stiffer rod string. Allows you to really achieve what your surface stroke's doing. But as this well declines and changes, that's the biggest change that we're going to make, is updating spacing. As an operator, it's a really good best practice. So we talk about applications, high volume wells, earlier post-flow or ESP transitioning to rod pumps, reducing the production gap between submersibles and rod lift, high deviation, reducing power consumption, high dogleg severity. With a long stroke unit, just due to the reduction of a residual motion of these units, we're able to reduce dynamic loading on rod strings. So you'll see in a typical 10,000, 11,000, 12,000 application, we can produce a well with a 366 or 416-inch long stroke with 86 tapers, just KDs or high strength rods. That in a normal, maybe a conventional 912 application, you'd be exceeding the rod loading by maybe 30, 45%. And again, that's just due to the slow strokes. It's reducing all those dynamic loadings just because you're not having a major pull on that unit. So again, reducing power consumption, high dog leg severity, wells prone to rod and tubing failures, and higher GLR for rod pump wells. It's kind of your application. But I think that was my 20-minute allocated time. Any questions, guys, or anything you want to talk about?
What's the cost difference between what you're lifting in a particular well versus what you would need with a conventional pump?
Hey guys, the question was, what's the cost difference, CapEx cost? Downhole, your sucker rods and your rod pumps pretty much the same. I mean, you're using the same tapers. Your rod pump's going to probably be a little bit more expensive because you're using probably now you're using a 40-inch barrel compared to a 26-inch barrel. Surface, you're probably looking now with the market changes and the improvements in manufacturing, probably a 20% increase, between a 912 or 1280. A 640, you're probably looking at about a 50% increase in CapEx cost.
So your unit is that much more expensive?
Yes, dependent, and it's not just a Liberty unit. It's just the market. You think about raw materials in terms of a cost. A 320 reducer costs much less, but the mechanical components of that unit, you've got a little bit more of a mechanical options on the unit. It's on a beam unit, you've got your wrist pins, your saddle, your tail. Those are your main components. We've got a couple more bearings in it, but yeah, the cost is a little bit more. Any other questions, guys?
No, that's it. Want to thank Wes for coming out and giving a hand. Appreciate you coming out. A couple of things just to finish up, guys. We've got speakers every month through May to include next year in February. Base will be speaking in May, and then we have Viking Engineering that's also going to be speaking there in April and March. I'm only half the man as Sammy, so I can't remember. So thank you guys. I don't know, Randall, you got anything else?
That's it. Have a good week, guys.
Hey, thanks for coming out, guys.